slant asymptotes of rational functions. So we've done a fair amount with rational functions at this point, including both vertical asymptotes and wholes and horizontal asymptotes. In this video, our objective, we want to identify slant, sometimes called oblique, asymptotes of rational functions. So what do we know? Well, we know what a rational function is. It is the quotients of polynomial functions. So the rational function f of x is equal to the division of two polynomial functions, in this case p of x divided by q of x. And since we can never divide by 0, it's undefined, q of x cannot be 0. We know what a polynomial function is. It's a function of the form f of x is equal to coefficient times an x term plus coefficient times an x term, etc., plus a constant. And if it's written with exponents in decreasing order, it's written in standard form. And the coefficient with the highest power is the function's degree. The x of the highest power is called the function's degree. And finally, we know what an asymptote is. It's a line that guides the graph of a function, but is not part of the function itself or part of the graph. So what is a slant asymptote? Well, as you might imagine, it's a slanted line, which means it's non-horizontal and it's non-vertical. And every line has the equation y equals mx plus b. This is the equation of the line in slope-intercept form. So a slant asymptote is a slanted line that has the equation y equals mx plus b that guides the graph of a function, but is not part of it. Like horizontal asymptotes, slant asymptotes can be crossed. Also, like horizontal asymptotes, a function can have at most one slant asymptote. Okay, a very particular situation in which you have a slant asymptote. The graph of a rational function has a slant asymptote if the degree of the numerator is 1 more than the degree of the denominator. You will get a slant asymptote. Okay, how do you find the equation? How do you find this linear equation of the slant asymptote? We're going to do division. And I think I'm going to do one example with long division and one example with synthetic division. But you do division and you ignore any remainder, and what's left is the equation of the slant asymptote. So let's take a look. Two examples. Algebraically, find the equation of the slant asymptote of f of x is equal to x squared plus 1 divided by x minus 1. Now we want to notice, the degree of the numerator is 1 more than the degree of the denominator. Let's note that. The degree of the numerator is 1 more than the degree, looks like I got too close, sorry about that, of the little swoop down here of the denominator. Okay, so how do I find the slant asymptote? I do division. X squared plus 1 divided by x minus 1. Okay, so let's recognize I'm missing the x term here, so I need to put a 0x in there in order to do division. So x squared plus 0x plus 1. And we learned all this as we did division of polynomials. X minus 1. Okay, x goes into x squared x times. I'll write the x in the x column. X times x is x squared minus, well, 1 times x is x. I use parentheses, and then I subtract. The parentheses help me keep track of double negatives. And of course, I know this is nothing. This is 0. 0 minus negative x is 0 plus x. So this is x. And then this is x, and then I bring down the plus 1. Okay, x goes into x 1 time. 1 times x is x. 1 times negative 1 is negative 1. Parentheses, subtract. X minus x is 0, but of course we planned it that way. 1 plus 1 is 2. And as we know, this is the remainder. We're not worried about the remainder. It doesn't matter to us. Okay, so what do we know? We know that x squared plus 1 divided by x minus 1 is equal to the quotient, which is x plus 1. X plus 1 is the quotient. And we have a remainder, so it's plus 2 over, and of course it goes over the divisor, and this of course is our remainder. However, when we find the slant asymptote, we ignore the remainder. We're only looking here, okay? And so y equals x plus 1 is the equation of the slant or oblique asymptote. Right there. And it's always going to be linear because you're always only 1 degree apart here. So you're always going to have a line that comes out of this. Let's take a look at this graphically and see if we can see it. I believe we can. Let's clear out of here. So here is the equation. Again, it's a rational function. It's a division function, if you will. So I'll put in my division bar. The numerator is x squared plus 1. The denominator here is x minus 1. Okay, let's graph that. So here comes this function. And you can see that's what you got going on here. Okay, it's obviously split up. Now, if I go into y equals, you can see, I'm not sure, I don't think there's a vertical asymptote because, yeah, there is a vertical asymptote at 1. So we can see the vertical asymptote is, but there's also a slant. You can see what's going on is a line is shaping this direction. Let's go back to y equals and go to y2 and put in the equation of our slant asymptote, x plus 1. And you can see how it's shaping it. Okay, we graph. And so there's that slant asymptote that is shaping the graph as x goes to positive infinity. If x goes to positive infinity, it's getting closer and closer to that line without touching or crossing it in this case. And as x goes to negative infinity, it's getting closer and closer to that line again, in this case, without touching it. So it's shaping the graph it's shaping the graph for us without being part of the function. And again, we note here that we have a 1 that's not part of our domain. In this case, x equals 1 is a vertical asymptote, and you can see that shaping it vertically right here. Okay, let's do one more example, and we'll use synthetic division to do this one. Just to kind of pull back and remind ourselves how some of that stuff works. Okay, so our second example, algebraically, find the equation. I think I got my paper straight. Find the equation of the slant asymptote, f of x equals x squared minus 4x minus 5 over x minus 3. We want to notice that our numerator is 1 degree larger than our denominator. So we have a slant asymptote. Okay, and we notice 3 is going to be either a whole or a vertical asymptote. I haven't divvied this thing up yet. I'm not sure if I can. 5 and 1, maybe I can, but I don't think it gives me a 3. So I think 3 turns out to be a vertical asymptote in this one too. But we're focused on the slant asymptote. The degree of the numerator is 1 greater than the degree of the denominator. Let's divide using synthetic division, x minus c. And so in this case, c is equal to 3. And so we'll put the 3 out here, and we're going to divide that into this numerator, which has coefficients 1, -4, -5. So I'll write those coefficients down. I'll bring the 1 down to row 3, and then I'll start my algorithm. 3 times 1 is 3. 3 goes into column 2, add, -1. 3 times -1 is -3. I'll write that product in column 3, and I'll add, and I'll get -8. I'm done. This is my remainder. Okay, so what do I know? I know that x squared, oh yes, and this is my quotient, or the coefficients of the quotient. X squared minus 4x minus 5 divided by x minus 3. Well, that's equal to the quotient. These are the coefficients. This is x, 1x, and this is minus 1. So I'll put a dotted 1 in here for you can see it. There's that 1. So 1x minus 1. This is the quotient. Plus the remainder. The remainder in this case is -8. And I'll write that above my divisor, x minus 3. Again, just so you see and remember all these pieces. Okay, so that's the answer. This minus this is equal to this quotient plus this remainder. When it comes to slant asymptotes, we ignore the remainder, and the quotient is the equation of our line. So let's see here. The quotient, let's write that down. The quotient is the equation, okay, of our slant or oblique asymptote, which is going to be y equals x minus 1. Okay, we're focused here. Let's take a look at this one, and then we'll be all set. We'll see how this one works. Go back into y equals, and we'll clear out those two. Okay, here's my equation. Again, it's rational, so I'll start off with my fraction bar in my calculator. X squared minus 4x minus 5 in the numerator, x minus 3 in my denominator. And let's graph that. Let's remember that 3 is going to be a vertical asymptote. So now you can see x equals 3 is shaping this graph right here. That's a vertical asymptote. We knew that up here because we had 3, a 0 in the denominator that did not cancel with anything in the numerator. Okay, and y equals x minus 1, so go back into y equals an equation 2 in red, and we'll put an x minus 1, and we'll see how that line is shaping the graph. So as x goes to infinity, the graph is getting closer and closer to that slant asymptote, and as x goes to negative infinity, the graph's coming down and is getting closer and closer to that line y equals x minus 1. So there you have it. We've done it all. Horizontal asymptotes, vertical asymptotes, and slant asymptotes. Slant asymptotes, as a reminder, come into play. Okay, as a reminder, they come into play when the degree of the numerator is 1 more than the degree of the denominator.